This video is part of a series of presentations covering the key concepts of multithreading and synchronization. This presentation in specific covers the basics of measuring timings of multithreaded programs using the USR bin time utility in GNU Linux. It also covers understanding the basics of timing statistics to draw some inferences about the effectiveness of multithreading. Developing good multithreaded programs presents several challenges. First, we have to work on understanding how to subdivide the problem into multiple threads so each thread has some work to do. Then we have to choose the number of threads appropriately based on the hardware that we have available and of course the software characteristics that we are trying to work with. Some of the programs need to coordinate or synchronize these threads that can pose additional challenges. Hence, testing, particularly testing multithreaded programs, is a very important concept to keep in mind. There are two types of testing. First one is, of course, functional testing, where we ensure the multithreaded program is producing the correct results. The second part of testing is called performance testing. This type of testing is used to assess if the program is running efficiently on a given computer. This presentation focuses on basics of performance testing of multithreaded programs. Keep in mind, performance testing is an important aspect of multithreaded programming. This performance testing phase should never be ignored or skipped, particularly for multithreaded programs, in order to ensure efficient and correct multithreading. Timing a multithreaded program provides a simple and effective approach to assess the overall performance of a multithreaded application. GNU Linux provides a GNU system utility called USR bin time that prints the overall aggregate timing statistics for any given program or process that is being run. So for example, the way USR bin time works is that it first forks itself to create a child process, and in the child process, it executes the command that's being supplied. You can supply any command with any command line arguments, and USR bin time will run that command with those command line arguments. Once the program is done running, the time command will wait for the program to finish and then collect the system resource utilizations or resource usage from the Linux kernel and print it. The kernel measures these timings using CPU clock ticks, which is typically the highest precision information that you can get on most modern CPUs. To get additional information, you can look up the man page for wait3 system call and also look up the get r usage system call, or you want just simple times, you can use the time system call, and you can find information about these system calls via the Linux man pages. Using USR bin time is pretty straightforward at the bash shell. So let us say you want to measure the timing of, say, the ls command. So you would type the command ls with whatever command line arguments you want and simply add USR bin time at the beginning of it. You would typically first see the output from the command that's being run. So this would be the normal output that would be generated by the program. And then you will see output from USR bin time, which will give you statistics about the behavior of the program. You can also discard the output of the program using redirection. This is useful to reduce clutter or output from the program and focus on the timing data that is generated by USR bin time. So in this case, you can run the command and simply redirect the output to /dev/null. The /dev/null is a special write-only file. This is created by the kernel, and any data that's written to it is simply discarded, so you will not see any output on screen. However, you will see the output from USR bin time because it is written to standard error. So you will see the output, and you can now focus on the statistics that is generated by USR bin time for analysis. Note that here we are specifically and explicitly referring to USR bin time to avoid confusing or accidentally using internal or built-in time commands that are often available in shells. The USR bin time command can also print the output and statistics in a slightly more verbose format. For this, you can use the --verbose or -v flag. Keep in mind the statistics are the same whether you print them in an abbreviated or in the verbose format. So when you run a command, say with -v or the verbose flag, it'll basically print the statistics with additional descriptive messages about each one of the statistics that was generated. In the rest of this presentation, we are going to do a deeper dive on the meaning of these statistics and how to interpret these statistics and draw inferences about the multithreading properties of programs. So given that there's no difference whether it's abbreviated or the verbose format, let's do a deeper dive into understanding these timing statistics. There are four key statistics to keep in mind in order to assess the performance of multithreaded programs. The first one is called user time, which indicates the total time that the CPU spent for running all of the instructions in the user's code. So here, the user time indicates the CPU time that was spent to execute instructions specifically in user space. This is the user time spent in running the program in user space, and this is the sum of the instructions or time spent by all of the threads. So it is the sum of the times and not data for just one thread. This value is only mildly influenced by other processes running on the system. This is because the number of instructions that are going to be executed in a program is independent of the other processes that are running on the system. The next data point to look at is the system time. This is the CPU time that was taken to run instructions for syscalls made by the program. Keep in mind that syscalls are calls to the operating systems that are used to perform various operations. This includes creating or starting and stopping threads. Any input-output operations that are performed by the program or threads is also done by the operating system, and these instructions are all accounted under the system time that is reported by USR bin time. And of course, similar to user time, this value is also not only mildly influenced by other running processes, because the instructions that are executed by a program are not dependent on other programs or processes that are running on the system. The third data point to keep in mind is elapsed or wall clock time. This is the runtime of the program as would be observed or perceived by an user. That means if you run a program and you use a stopwatch, this is the time you would observe that the program took to run. This value, the elapsed time, is heavily influenced by other processes due to multiprocessing. Keep in mind, if you have many programs running on a system, they're all utilizing or sharing time on the CPU. So the time taken to execute instructions can be higher if there are more processes running on the machine taking CPU time. However, on lightly loaded machines, that means on that computer, this program was the only program that is heavily running and heavily using the CPU, the elapsed time will be repeatable. That means every time you run the program, you will get almost the same runtime or elapsed time. Keep in mind, it will be almost the same. It will not be exactly the same due to other system processes and such that are running on the computer. So it's not that it's your only program that's running. It's just it's lightly loaded. That means majority of the time was spent running your program. So the timings will be very repeatable. That means very close, but they will not be identical. The next statistic to observe is the percentage CPU that has been utilized by the program. This value indicates the average number of cores that was utilized by a program. So in Linux, each core is accounted as 100%. So if a program uses 3 cores all the time, Linux will show that it used 300% of the CPU resource, or it used 3 cores on the CPU on average. On lightly loaded machines, this value, percentage CPU, is a good rough estimate of the number of concurrent threads that were running in a process. So if you see CPU time as 300%, that you know that at least 3 threads, there could have been more threads, but you know for sure at least 3 threads were running at any given time using 3 cores on the CPU. On lightly loaded machines, this is important. That means on this machine, the given program was the one that was predominantly running at almost all of the time. If you have a well multi-threaded program, the percentage CPU being reported should be very close to the number of threads. Keep in mind the percentage CPU will never exceed the total number of cores, and the percentage CPU will not be exactly equal to the number of threads, but it will be close. So that means you will see 100% CPU if it's one thread, 200% CPU if it is two threads. So for example, you have three threads, you will see a value that is close to about 300%. Typically, it will be close but not quite. For example, in this case, it's 290%, which is actually pretty good, because it does take some time for the program to start threads and for the threads to finish, and maybe the program is doing some input output operations before and after the threads. Those are running in single threaded mode, so getting close to 300% for three threads is pretty good. If you have four threads, you should see 400% on a 4-core CPU. But keep in mind the percentage CPU will never exceed the total number of cores that are available on a given CPU. If you have poor multithreading, then the percentage CPU would be much lower than the expected number for a given number of threads. So for example, in a poor multithreaded case, if you're say running 5 threads, you might only see about 100% or 200%, less than 500% CPU usage, considerably less, and that indicates that the program is not multithreaded effectively. Keep this caveat in mind: idling threads don't use CPU, so if threads are waiting for I/O operations, they will not utilize all of the CPU time. And also, this assessment or this approach or this statistic is not meaningful when a large part of the time of the program is spent only in single threaded mode. That means the program is running in multi-threaded mode only for a short fraction of time. So that means on an average, the overall percentage CPU utilization will be lower. So for single threaded or programs, or for programs where multiple threads are not running very long, this approach will not give you correct inferences. Addressing performance issues can be challenging, and this process of addressing performance issues is called performance tuning. Keep in mind the stats from USR bin time only provide a high-level summary, so you can utilize that on a lightly loaded machine to determine if additional performance analysis and performance tuning is necessary. When performance tuning, a software called a profiler is used. Profiler is a utility or a software tool for performance profiling. This is similar to using a debugger. Debugger is used for troubleshooting functional issues in a program, versus a profiler is used to troubleshoot performance bottlenecks in a program. Similar to debugger, working with a profiler requires some experience and some practice in order to be able to identify and troubleshoot performance issues. And utilizing a profiler is a reasonably sophisticated operation, and it's well beyond the scope of the series of presentations. This series of presentations so far has covered introduction and motivation for threads. We have looked at how to create and manage threads in a C++ program. This specific part of the presentation series covered the timing and measuring the performance and assessing the multithreading effectiveness of programs using USR bin time. Subsequent part of this series will focus on threading without synchronization and threading with synchronization using one or more resources, and also will cover the producer-consumer model in other parts of the series. Hope you found this presentation interesting and useful. Don't forget to check out the other presentations in this series.